I'm never sure if I phrased this problem correctly, but it gets the point across. We've got a boat in the water. The boat thinks it's doing one thing because its instruments say it's going a certain speed on a certain heading, but the current is pushing the boat along. And so from above, we can see that the boat is actually going to be doing something else. So there's what the boat thinks it's doing, what the current is doing. This is a perfect problem for vectors because what the boat is actually doing will just be the sum of the vector of the boat and the vector of the current. So we have a vector for the boat. We have a current vector. And we've got the actual vector. So the course vector is just the boat vector plus the current vector. So since the boat thinks it's traveling due east and the current is traveling due north, the two vectors make a right triangle, and we just need to use our skills in solving triangles to solve the triangle. So we make a right triangle here. We've got to put an angle in this somewhere. So I'm going to put my theta down here. And then so this 10 miles per hour is going to be opposite. 30 miles per hour is going to be adjacent. And the course, the length of this is going to be the hypotenuse. So we're going to use the opposite and adjacent to solve for theta and solve for the hypotenuse. And that will tell us the actual course of the boat. Any questions? One of the things that we want is the hypotenuse. We can get that with the Pythagorean theorem. So the hypotenuse squared is going to be the opposite squared plus the adjacent squared. So that's going to be 30 squared plus 10 squared. So the hypotenuse will be the square roots of 30 squared plus 10 squared. We'll just grab our calculating machine, figure out the square root of 1,000. So square root of 30 squared plus 10 squared, 31.62. So the boat is moving a little bit faster, even though the current's not going with it. The boat is going 30 miles per hour horizontally and 10 miles per hour vertically. So overall, it's going to cover a longer distance. It'll cover 31.6 miles per hour. It'll be going at a faster speed because it's not just horizontal speed. It's also got some vertical speed that's increasing the speed of the boat. We also want to figure out what theta is. So theta has an opposite of 10 and adjacent of 30. So we'll use tangent. So tangent of theta is opposite over adjacent. So the tangent of theta is 10 over 30. So theta will be the inverse tangent of 1/3. So I'm going to switch my calculator to degrees and do a tangent inverse of 1/3, 18.4 degrees. So we're traveling at a speed of 31.6 miles per hour. Like we're on this boat. The boat is traveling at a speed of 31.6 miles an hour at an angle of 18.4 degrees. This angle of 18.4 degrees is with the horizontal. So we could, that's not usually how we would describe a heading. If we're going to describe a heading, usually we have some degrees measured east of north or west of north. We usually use north as 0. Standard position has horizontal headed to the right as 0, but for heading, due north is 0. So usually for heading, due north is 0. So heading is usually measured with due north as 0 degrees. And then we'll say east of north or west of north. Instead of using positive and negative, we'll say east of north and west of north. We do this on streets as well. We have one street in the middle, and then we can have West Fifth Avenue and East Fifth Avenue, because we don't want to just have positive and negative numbers. So we don't want to have one person living at 500 East Poplar Avenue, and then on the other side of the street in the middle, negative 500 Poplar Avenue. You don't want to just kind of like have positive numbers and negative house numbers. You know what I mean? That would be really weird. I don't know why. I wonder if it makes Cartesian coordinates more difficult that we don't want to have house numbers that are negative. But we have to have like an east and we have to have a west. Anyway, so for heading, we usually measure due north as 0 degrees. So if we say a heading of 0 degrees, that would be due north. And then usually we'll say east of north and west of north. So this angle of 18.4 degrees is inside the triangle. So our heading could be this angle, some amount east of north. So in this case, our heading would be 90 minus 18.4. Or 71 points, we'll call it 71.6 degrees east of north. question? Is everybody okay? So we could also imagine if we have the course of the boat, we can break the course of the boat down into two component vectors, a horizontal and a vertical component. Here we were given a horizontal and vertical component, and we were asked to find out the resultant vector. That is, given an adjacent and an opposite, find the hypotenuse and an angle. Goes back way back to the beginning of the semester when we were solving right triangles. So let's change things up a little bit. We're still going to have a boat going in the water, but instead of the boat and the current being perpendicular to each other, I'm going to have the boat going off at some weirdo angle, and the current will be going off at some other weirdo angle. Oh, not a bot, a boat. Same question, we want to find the actual course of the boat. We're given two vectors, a boat vector and a current vector. And we want to find the resultant vector. So here's what the boat thinks it's doing. Missed. Boat says we're going 30 miles per hour. We should mark where north is. And our heading is 100 degrees east of north. So we're actually traveling a little bit to the south east. But we've also got a current. And the current is 20 degrees (10 miles per hour) at 20 degrees east of north. And we want to use this information to calculate the resultant vector. The difference between this problem and the previous problem is that we no longer have a right triangle. So, well, unless I messed up, we'll find out. So here, we don't want to say things like opposite, adjacent, and hypotenuse because we might not have a hypotenuse because we might not have a right triangle. Let's figure out how what kind of angles we have. Notice that the 100 degrees is not an angle that's in this triangle. That 20 degrees is not an angle in the triangle. We do know that the sum of the angles is 180 degrees, but I don't have an angle in the triangle. I've got a piece of an angle in the triangle, this 20 degrees, but I'm not even sure that the course is going to be above east. I don't know if that 10 miles per hour is enough to push our course above due east, like I have it drawn. So let's figure some stuff out. I want to look at this piece of the triangle, or this small section of the triangle. Because here, I can draw a right angle. So I'm going to pull out this piece of the triangle. Now, this 30 miles per hour is 100 degrees east of north. So here's north at 0, and we go 100 degrees towards the east. So we've gone past due east. How far past due east have we gone? What's this angle going to be in here? There's the vertical. There's due north. We've gone 100 degrees east of north. It's 90 degrees between due north and due east. So how much is this angle in here? What's this little piece? It's 90 degrees from north to east, and we've gone to 100 degrees. That means this angle here is 10 more degrees. If that angle in there is 10 degrees, then in this right triangle, we can figure out this angle is 80 degrees. So I can break those pieces apart. Then I just have to take this information back to my original. And so now that angle between the boats, what the boat thinks it's doing, and the current, that angle is 100 degrees. Now I have two sides of the triangle and one of the angles in the triangle, and that means we can solve the triangle. We're going to have to use different tools than we did for our right triangle in the previous example. So let's draw the triangle that we have. So we're trying to solve this triangle. We've got two sides and the angle between those sides. So I gotta name some stuff. Let's call this angle, let's see, usually I went alpha, beta, and gamma. So this is gonna be angle gamma. This will be side C. This is usually side A. And so this is going to be angle alpha. So 30 could be side B. And that would mean this up here is angle beta. So I have three pieces of information. I got A, B, and gamma. I don't have an opposite set of parts, so I can't use the law of sines. I also can't use anything with hypotenuse in it because we don't have a hypotenuse, we don't have a right triangle. Since I don't have a set of opposite parts, we have to use the law of cosine. We don't have a set of opposite parts, so we're going to have to use the law of cosines. So the law of cosines for side C, since we have angle gamma at 100 degrees, law of cosines for sine C will be the square root of a squared plus b squared, so a squared plus b squared minus 2ab times the cosine of gamma. So I have the square root of a squared, b squared minus 2ab times the cosine of gamma. Any questions? How's everybody okay? The angle that will be involved in the heading would be the angle alpha. So let's use now that we have side C and angle gamma, we could use that information to find angle alpha. So sine of 100 degrees over C is equal to the sine of alpha over A. So sine of alpha will be 10 times the sine of 100 divided by our 33.2. So we'll have a sine inverse of 10 times the sine of 100 divided by the 33.2. I don't want to round it off, so I'm going to hit second answer, close parentheses on the sine inverse, and hit equals, and that angle alpha is 17.2 degrees. We want to transfer this into a heading. So if we draw what's going on at the tail end of the boat, we know we've got the boat at 100 degrees east of north. Here's 90 degrees east of north, which means this piece in here is 10 degrees. The angle between the path of the boat, what the boat thinks it's doing, and the actual course is 17 degrees. So angle alpha will be 17 degrees. So it looks like the actual path of the boat will be 7.2 degrees north of east. So the actual heading for the boat, if we just do 100 minus 17.2. Any questions? How's everybody okay? Everybody looks stunned. They're like, oh, so we can avoid trigonometry by never going on a boat? Yeah, probably. So the point of the problem was to understand that the resultant vector is going to be the sum of the boat's vector and the current's vector, and then just use the things that we already know about solving triangles to solve a triangle. How's everybody okay? Right now, the quizzes that we have are all just generic triangles. There's no situations where you have to break things down or calculate headings. You just have to figure out the stuff inside the triangle. But here's one place where we might be applying what we know to some situation. It always happens in math classes. You start learning a thing. It's like, oh, when am I ever going to do this? Or what can this be used for? It's like, oh, here's an example of solving triangles in some kind of practice. And then some students are like, oh, I bet I need to make it more personal to avoid this. Like, well, when am I ever going to need to know how to do this? Why don't I just use GPS? Well, yeah, that's actually how we should do things. Just use GPS. But the good news is when you're in a math class and all of a sudden you start wondering, So like all of a sudden, the most important question is, when am I ever going to do this? And you think, I'm going to hit the teacher with this gotcha question. Because students, when they ask, when am I ever going to do this? Always ask it in a manner that suggests they think they're the first person to ever ask the teacher that question. As if I haven't been teaching for well over 20 years at this point. I get that question quite a lot. So they'll be like, when am I ever going to use this information? As if the teacher is going to hear that question go, oh, I've never thought of that before. Everybody asks that question. Here's what that question really means. You're not actually worried about when you personally are going to need to solve a triangle. What we need to recognize is that is not the issue. The issue is you are annoyed that I'm asking you to know a piece of information and you don't want to know it. The reason that you don't want to know it is that you just recognized, oh, this is kind of tricky. I'm going to have to figure this out, and it's going to take time working on problems that I don't want to solve. That's your mind telling you, it's like, oh, this didn't come easy to you. This problem didn't come easy to you. You're going to have to spend some time thinking about this. And then the other part of your mind saying, and we don't want to do that, do we? And then the rest of your mind going, no, we don't. We would rather go play Xbox. It's like, well, we need a reason to justify not doing this. And then the Xbox portion of our brain is like, oh, just ask the teacher when we're ever going to have to do this. Then I just use my experience to cast Shield, Teacher Shield. And the verbal component of casting Teacher Shield is, that's not the point. The point isn't that I'm training you to do something that you're going to do later on, right? The point is that we understand how math works and that we gain some proficiency in mathematical things. This is kind of important because math is quite often weaponized against you. Very often, math is going to be weaponized against you. And it's happening all the time. I don't know if any of you have a social media account, but if you have a social media account, math has been weaponized against you. An algorithm is deciding what stuff to show you. And that algorithm knows what kinds of things will make you angry. And it shows you those things. It knows what's going to make you angry, what's going to get you to click on stuff. And it's going to show you those things because it wants you to be angry. I want you to be happy and calm that you can solve problems. But your phone wants you pissed off because pissed off people engage on their phone and thus see more advertisements. Math has been weaponized against you. Any questions? Comments? Any thoughts? Some of you might go, it's weaponized you in not just algorithm ways. Some of you might in the future go try to buy a car. And you're like, oh, wow, $40,000 is way too much for a car. I'm going to go find a car that I can buy for under $1,000. And they're going to say, well, here, look, if you just do this, sign this paper, and your payments will only be $200 a month. And you're like, oh, okay. $200 a month I can handle. Yeah, so here you go, $200 a month for the next 10 years. And you're like, oh, wait, what was that? So nothing, never mind. Ignore that part. You know what I mean? Anybody driving Nissan? Anybody? Nissan? Did everybody buy it new? That's good because they'll be like, well, oh yeah, here's 8 years. You can take a car and pay for it over 8 years. And your monthly payment is going to be low. And when you walk in at your ages to a car dealership, they are not going to talk about the price of the car. They're going to say, not what you want to spend for the car, which is the number that you need to know. They're going to say, how much do you want your payment to be? And they probably have a plan for that payment. That makes sense? This is how you buy a $40,000 car for $60,000. So it's not about solving triangle. It's about being proficient in math and knowing when math is going to be used against you, weaponized against you. How's that, okay? Does anybody have social media accounts? If you're at all depressed, one of the first steps is get rid of your social media account. They're just pissing you off. The only reason I still have Facebook is I have friends, and those friends have dogs, and those dogs are old. And I need to know. I don't read it. I only check, see if my friends have posted anything. Oh, shit. Because you can't just like walk up to someone they haven't seen for months, knowing that they have an old dog, and say, hey, how's Finn? Right? You got to think about it. There's math that goes on here. It's like, well, Finn is a fairly big dog. And the last time I saw Finn a year ago, he was 12. So you got to know that. You can't just bring that shit up. You know what I'm talking about? Like if you know, like last year they just got a puppy, it's still pretty dicey because some shit may have happened. You know what I mean? You're kind of safe. It's like, oh, hey, how's your puppy? And you're kind of safe. Now, if you think I'm blowing things up, it's like, oh, this is just too much. Replace puppy with baby. And think about how awkward that conversation would get if you haven't been paying attention. Right? So, but like, don't like sit there and scroll and get your news from that source. That's terrible. It's just trying to piss you off. You know what I mean? All right. This is the thing about vectors. We want to just add a couple of vectors to figure out a resultant vector. That's going to be, we've got one more major thing after vectors, and it's complex numbers. And I think the only reason that I do this is because I think it's fun. You will all not think it's fun, but I think it's super fun. So tough. All right, that's going to do it for today. That's going to do it for this week. I'll see, or no, it's Tuesday today. That's going to do it for today. I'll see y'all on Thursday. We're going to have a good couple of days, and thanks for playing.